Okay guys, let's get started on the topic chemical energy changes, and this is going to look at when a reaction takes place. Why does it take place? How does it take place? What are the conditions for it to take place? And you will notice, and this is a very interesting and important thing to understand, is that when we do have molecules that are trying to react with one another. So there I have one molecule. Okay, so let me just get it a bit darker. I have one molecule, and this molecule is going to react with another molecule. Let's make that one different. And so let's say this is, for example, oxygen. This is oxygen, O2, and that's hydrogen, H2. And now oxygen, if it reacts with hydrogen, it is an exothermic reaction. We'll look at that just now. But when these two things react, it produces water. So hydrogen. Yeah, so there's my water molecule that's being produced. Sorry, two of these. So that we now have H2O. H2O. Now you'll notice, in order for these two molecules to produce that molecule, now there will be two of these molecules produced for every oxygen, because you'll see H2O, water, has one oxygen molecule, but oxygen itself comes as a diatomic molecule. It has two, so we will need two hydrogens for every oxygen to react. And that is why when we have the reaction of oxygen plus hydrogen, if we write it as a reaction, we will write it as H2O. Then we need to count, and we'll see we need two of these, because there's two oxygens on this side, and now we've got four hydrogens, so we just need to add another two there so that we have four hydrogens. Okay, and this just literally means for every one molecule of oxygen, we have two molecules of hydrogen, and that produces two water molecules. But notice what needs to happen in order for this reaction to occur. First, we need to break this oxygen bond. Now, this bond, because this thing is bonded, and because we need to break this bond, obviously to do anything we need energy. So if I wanted to break this bond, I will need to use energy to break that bond. Now that means that it already has energy keeping it together. Okay, a potential energy keeping this molecule together. Now this one, you'll also notice that this one also needs to break, because part of it, one of it attaches to oxygen on one side and another one attaches to oxygen on another side. Okay, so it too needs to break. Yes, both of them are going to form a new molecule, but so this one also therefore has. So this is going to be the reactant, a reactant potential energy, and this is a reactant potential energy. Now afterwards we have a molecule again. Now again, all of these atoms are being held together, which means if I wanted to break it, I will need energy, which means it itself has energy that holds it together. Okay, and that would be again a potential energy. It's energy that it contains, holding things together. So for example, if I hold something up in the air, it has the potential to fall, isn't it? And falling would be kinetic energy. So while I'm holding it, I have the ability to convert some energy into another energy. It's just not being converted now, but it has that potential. Now same thing occurs here. Now this we will call the product's potential energy. Okay, now if I then look at all of the energy that my reactants have, okay, that would be called, the reactant energy would be now the sum of those two, just all of the energy that each molecule contains. And then afterwards I have the product's potential energy. Now it's not necessary that both of these energies are the same. The energy that oxygen has plus the energy that hydrogen has as molecules is not necessarily the same than the energy that's needed to keep water molecules together. So if this reaction happened and these two, the total energy on this side, the total energy on this side, and the total energy on that side must still be the same. So if the potential energy on the left is not equal to the potential energy on the right, there must be an excess of energy somewhere. And where did that energy go? It is given off in the form of light or heat. Okay, so the extra energy is given off in the form of, in this case, the energy to keep water together is less than the energy to keep oxygen plus the energy to keep hydrogen together. So afterwards, the extra energy that this has, some of the energy goes into potential energy, the rest is given off as heat. And this is when we will have an exothermic reaction. In other words, in an exothermic reaction, the amount of energy that the reactants have is more than the potential energy, not equal to, is more than the potential energy that the products have. In other words, the energies keeping the molecule together for reactants were more than the energy. So the extra energy, because they were broken, some energy was used to form the water, the rest of the energy is given off in the form of heat.
So energy was released in exothermic reaction.
Yeah. So in an exothermic, this is exothermic reaction. Now let's look at something like Haber process. So in the Haber process is the production of ammonia. So it's hydrogen plus nitrogen producing ammonia. Okay? Now, in this reactant, you'll see that on this side we have one. Okay, let me fix that. Should be NH3. So in other words, on this side we see we have only one nitrogen and we've got two nitrogens there. But if I change this one to 2, notice that now I have 6 hydrogens, and here I only have 2, so I just need to multiply that with a 3. Okay. Now this one, so this one is once again just an example of an exothermic reaction, which means that the energy that is used to keep hydrogen and nitrogen together, the total energy here would be greater than the energy keeping nitrogen and hydrogens together. Okay. Now, one thing that you'll notice is what we call the heat of a reaction, the enthalpy. Enthalpy is the difference between the potential energy of the products minus the potential energy of the reactants. Remember, whenever we take the change of something, it's future minus initial. So it's kind of the same. Product is what I get in the future. Reactant is what I had in the past. So enthalpy is just the product, the energy in the products minus the energy in the reactants. So if I notice that my product, my future energy is less than my initial energy, you'll notice that for an endothermic reaction, my enthalpy will be negative, because I will have a smaller number divided minus a bigger number. So I'll get a negative answer. So my enthalpy, and that's why if we look at the Haber process, for example, you'll see they give you the enthalpy here. Enthalpy. This is how much kilojoules, negative 92, okay? That's how much kilojoules will be released. So the negative means it is released into the system. We're losing energy in the system. Negative 92.4 kilojoules for every 1 mole of product produced. So per mole. So that's how much kilojoules is released for every 1 mole of product released. Okay? So that will be for an exothermic reaction. Now, one more thing that I want to show before I give you an example of an endothermic reaction is when we do an energy diagram. So in an energy diagram, we will have our potential energy here on the horizontal axis, and our time would be here, sorry, on the vertical axis. Our time, it's not really time, they very seldom name this axis, but we can look at it as time on the horizontal axis. And what you'll notice is that for our reaction to happen, we obviously start, in the beginning we start with the energy of the products. So this would be the energy of the reactants. So at some point, then afterwards, for an exothermic reaction, we will have energy, but it will be less than the energy that I started with. Okay, so this would be the potential energy of the products. Now, in between here, something needs to happen. For one, is we need to break this bond. Now, in order for us to break a bond, we need to put energy into the system. No matter what type of reaction is, it always requires us to put energy in. So if we look at the total energy in the system, at some point we need to put in energy. So what is called the activated complex. The activated complex is the total amount of energy that that system needs in order to break the initial bonds. Okay, and this energy between here and there is the energy that I need to put in. Okay, so this is called the activation energy. Activation energy. That's the energy that I need. When I want to conduct this experiment, I need to put this amount of energy in, and that will increase the total amount of energy to a certain height so that the energy inside is enough to actually break this bond. The moment this bond starts breaking, the potential energy that it had is being released in the form of heat. Okay? Now, it doesn't mean it's being released in the atmosphere. It's just there's now energy, and this energy is now enough to start creating the new bonds. But as new bonds are now being formed, the energy that was released is being used up. So the total energy are now being used up, and now all of a sudden when I get here, the same amount of energy that I had, okay, all of the rest of the energy that's being released, instead of going into producing bonds, okay, so once I have enough energy, all of this energy is being used to break the old bonds, and new energy is now being used up to form the potential energy. But this energy here, this is the extra energy that I have left. In other words, this is the enthalpy. Do you see? So this is the energy that I started with, so I end with. This is the energy that I started with, so the difference, the distance between these two values is the enthalpy. And this is an example of an energy diagram drawn for the activated complex. Oh, sorry, drawn for the exothermic reaction. Make sense? Any questions? So far, this is not difficult. Okay. So Next is, let's just look at an example for endothermic. Okay, I think actually a very cool example for an endothermic reaction is photosynthesis. So for example, in photosynthesis is where plants use water and from the ground and carbon dioxide to produce oxygen and sugar. So that's, for example, why fruit would be sweet, is because of the sugar it produced through okay, so the sugar that's produced through so in other words, this is what the reaction looked like. It takes carbon dioxide, can you read there? Carbon dioxide plus water, okay, and it produces sugar, which is usually carbon H2O plus, and there would be a number of this would be a big carbon, usually roughly about 12 of these carbons are linked together. So let's take a link of 12 of these. Is it 12? 11 of these, and then plus carbon dioxide releases oxygen as well as more water. Okay, so you see we'll need 11 of these because we've got 11 carbons. We need 11 carbons on this side. On the water side, notice that we have water here and we have water there. There's an H2O here. So there's 11 waters being used here and one water there. So in total there's 12 waters. So we'll need 12 waters. Or I'm actually doing something wrong. There is oxygen. Oh yes, no, I'm correct. Okay, so it is 12 waters, and then the oxygens here, the CO2, there was 11 oxygens here, and this bond was broken, and there are now 11 oxygens being released. Okay, so again, this is photosynthesis, and you'll notice that is it what is it called? Chloroform. It is. It's in the plants that does this. But anyway, that's green. But it needs sunlight in order to occur. Okay. So in other words, part of what it needs is not necessarily heat, but photons. Okay. It needs light, which is a type of energy. It needs photons. So in other words, the energies that we have to start with, the potential energy in the reactants and the potential energy of the products. The products in total, their energy is more than I have in my reactants. So in order to have this reaction happen, we need additional energy in the form of photons, which is small packets of energy really. Okay, so if we had to draw that energy diagram, we would start with less energy and we would end with more energy. And now you'll notice that again, in order for this reaction to happen, we need to actually add a lot of energy into this system so that the activation energy for the activation energy, this is the potential energy in the reactants. Okay. This is the potential energy in the products. The difference here is the activation energy, and the difference here between these two, what is that again? The enthalpy. That's the enthalpy. And notice now that my products are higher than my reactants. So enthalpy, which is products minus reactants, I will now get a positive answer for. Does that make sense? So a positive enthalpy will tell me that I'm working with an endothermic reaction. Energy needs to be put in. The N prefix means in. The X prefix means out. Okay. So if we look at the exam question, this was question 5 in the exam, was related to what we spoke of just now. Okay. So you'll notice here, this is the potential energy on the vertical axis, and time on the horizontal axis. And first of all, just looking at that energy diagram, what type of reaction is that? Endothermic or exothermic? Endothermic, because the reaction, the energy I start with is less than the energy that I need to end with. So I'm going to need to add energy. Okay, so that's simple enough. Okay, if we had to redraw this now, and we had to name these, where's the reactants, the product, the activation energy, and the enthalpy of the reaction? Okay, where would we put what? So we have to do products. Let's make this smaller. Products. Can you read there? So that's reactants, products, activation energy, and enthalpy of the reaction.
Would the reactants be at the start of
the reactants we'll name here.
And then the products be at the end. Yeah.
There at the end, we'll write products there at the end. Activation energy.
be the difference which is in between the two?
Between what? These two?
Yes, the reactants and the products.
No.
No, that's enthalpy.
That's enthalpy, yes. So enthalpy is the energy that's being released or absorbed. And that's the difference there. Activation energy is the energy that I have to put in to start breaking the original bonds. Okay? And that means this is the difference between, that's the activated complex. That's the energy that we need to break bonds. The energy that I therefore need to put in is the difference between here and there. Make sense? Explain the effect that a catalyst will have on this reaction. Okay, so let me quickly go and show you what does a catalyst do. So if I put a catalyst in a reaction or add a, that's a bit big. If I have a molecule here and I need to break these bonds, and I need to, let's say I want it to react with okay, let's actually use this example, the example of nitrogen and oxygen, the Haber process example. You'd remember we said that the Haber process is an exothermic reaction, but we need to add we need to add energy still to reach the activated complex. Okay, now what happens is the moment I put in, now it seems that the catalyst that they use for this reaction is iron promoted with some sort of metal oxide, but let's just assume that we're only going to use iron for this example. So we have iron molecules in this reaction as well. Now what would happen for this reaction to occur is that the bond is going to break and the new reaction is going to form, but first it is going to be easier for the nitrogen, just name this, for hydrogen and nitrogen. I'm not exactly sure which one happens first or what way around it does happen. You don't need to know for the extent of this of metric chemistry, but for example what might happen is that the iron will react with the nitrogen. The iron will react with the nitrogen first. Now, for us to break this bond with enough energy to fuse with the iron is less energy needed than for, and okay, so what will happen is first nitrogen and iron will bond, but then this bond will break, and then this new molecule, whatever that is, I'm not sure exactly what it would be. It would probably be nitrogen. I'm not going to go into what it is exactly, but it's a molecule with iron and nitrogen in, and now this molecule will again break its bonds, and then this molecule will maybe fuse with the hydrogen. Again, I don't know which one happens. Is it which one reacts first? Is it nitrogen and iron, or is it hydrogen and iron? It doesn't really matter, just as long as you understand that there's an intermediate molecule being formed. So in between, instead of going directly from nitrogen and hydrogen and immediately forming ammonia, instead of going there, there's this intermediate molecule being formed. Maybe it's some iron nitride, or some sort of hydrogen and iron bond. Hydrogen and iron bond, I don't know, but there's an intermediate molecule. Now this molecule, these two molecules, or maybe this one and hydrogen, or this one and nitrogen, maybe both of them gets formed, but this reaction going from one of these to there, obviously that's now a different reaction also happening, but in the end all of the iron that we started with is returned. Iron is both a reactant and a product, but all of the iron that was in as a reactant is also a product. It's not like in photosynthesis. Notice here in the photosynthesis, yes, we had 12 waters. Water was a reactant and water was a product, but only one part of water is a product. So for example, a plant does give off vapor, water vapor. So if you were to put a plant in a sealed container, you would see it start forming precipice on the side, condensation on the side as it's releasing vapor, but it will use, for every 12 liters of water you give it, it will only release 1 liter of water. So this is not the definition of a catalyst. A catalyst would have both. In this case, we would have nitrogen plus hydrogen plus iron producing NH3 plus iron, and for every one iron, I don't know what would the relationship be, how many of these irons we might need, but all of the iron will be produced again. Okay, now just so that you understand, if we now take the total potential energies of the reactants, okay, and if we now take the total energy of the intermediate products, so let's call that UI, that's the intermediates, and we take the total energy of the products, UP, okay, the amount of, if I had to draw just this reaction here, that first between the intermediate state, I would have my products, my reactants starting, then I need an activated complex, but the amount of energy that I need to go from my original products, reactants, to my, and this one must be lower because it's an exothermic, so this is the original, this is going from nitrogen and hydrogen all the way to ammonia. Okay, now once I add a catalyst, the energy that I need to fuse, to break the bonds and fuse these bonds, and break these bonds and fuse the new bonds, is less than the energy that I would have needed to break this and fuse the original. Does that make sense? So in other words, the amount of energy that I need, the total amount of energy that I need, is less, in other words, the activated complex. complex is less. So what is the effect of adding a catalyst? A catalyst reduces the amount of energy needed to have successful, we'll talk about collision theory just now, but that's in the end what it comes down to. In order to have successful collisions, in other words, for particles to collide and form this, and then these particles to collide and form that, is less energy. The total energy there is less than the amount of energy that is needed for these two particles to collide and form this directly.
So in other words, does it like speed up the reaction?
It does that as well, because now the amount of energy that's needed is less. Yeah. So the number of we'll get to collision theory, and then I'll explain the catalyst's effect on reaction rate as well. But for now, in terms of energy, the amount of energy we can now see is that we need is less. It's almost like if you had to go and on that set of stairs, jump from the bottom of that stair to the top of that stair. Now, the amount of energy is not impossible. Someone might be strong enough, might have the ability to convert enough energy from his potential energy, the energy in his muscles, to catapult himself high enough to the top. But all of us can do it just by climbing the steps one by one. Do you understand? Going from one to, because it's less energy needed to go from one step to the next step. So the steps, in a sense, is a catalyst for a jump. Make sense? Okay, so you can look at it like that. So the amount of energy needed to go from here to there is less. Okay, so if we answer the question here in the exam, it asks, explain the effect that a catalyst will have on the reaction rate and energy in terms of collision theory. Okay, we'll look at reaction rate just now, but in terms of energy, what would you say? What does a catalyst do to the, in the words we've been using, what does a catalyst do? In terms of the graph?
It reduces the activation complex.
Activated complex. It reduces the activated complex. Now, when you reduce the activated complex, what else gets reduced? The activation energy. The activation energy is the amount of energy I have to put in to make this reaction happen. Does that make sense? So, by adding a catalyst, it reduces the activated complex. It's like climbing those stairs. By putting in stairs on a cliff, for example, I would need less energy to actually scale that cliff. So in the same sense, the activated complex and therefore the activation energy is reduced by adding a catalyst. We'll look at rates and we'll talk about rate of reaction just now. Okay.